Today I'm going to talk about a Flashgun trigger and delay unit that I've been developing over the last couple of weeks. Spent a bit of time on it, so I thought I'd document it. This is work in progress because it's not complete yet. Here are the requirements. Sense the trigger, trigger the Flashgun, and have a delay range from 10 microseconds to 1 millisecond. Going to use a PIC16F676 processor on Veroboard. This choice gives rise to some derived requirements. We've got to provide immediate output for calibration. I'm going to use 3 AAA batteries. I want an external power supply input, and I'm going to use resistor ladders to input the delay values into the system. Have a quick look at the program then. And this is Great Cow Basic. And basically defining a few parameters to start with. And then setting 1 or 2 pins, LEDs and whatnot. Then I'm going to wait for the arming button to be pressed, and at that point I'm going to start to read the values of the delay setting controls, which are read by the A to D converters from resistor ladders on rotary switches. And then the thing goes into the delay process as soon as the trigger's been sensed, which is done by the comparator on board. And there's various different corrections here for 0 delay, 10 microseconds delay, 20 microseconds delay, and then every other delay after that, and that's to try and cope with some of the errors due to the wait statements at short times. And it all sits in a nice loop. So that's the software. Next part is enclosure labeling. Now you may think, well, why major on this? Well, really the thing you tend to do is to decide what the person is going to see when they use the thing, and that kind of determines how you're actually going to design the equipment. So here's the front panel, various layers. This shows the box with its internal pillars that I've obviously got to miss when I put the components in. And then here are the radii for the various controls, the 30mm diameter that I'm giving for the rotary switches and the pot. And this is the drilling layer, which I'm going to use as a direct physical guide to drilling the thing. And here's the thing that the user will see, and that will sit underneath an acrylic sheet to protect it. You can see that there are these components of the delay, 1 millisecond, 100 microseconds and 10 microseconds, each in 0 to 9 steps. Trigger sensitivity is just a continuous part, and in fact it goes up to it goes further than the 9, but it doesn't really matter. On-off switch and power indicator, obviously, because they intend to be battery operated. The arming switch, which is push button, shows an armed light after that's been pressed. Then if you go manually triggered with the push button or externally triggered, it locks it out and waits for the next one and repeats the cycle. So I'm going to print these out, and the way I'm going to do that is print the thing from this program, which is Serif Draw Plus, as an export to PDF. And now I'm going to take the PDF file and print that from my other computer. Okay, now we're going to print out from Acrobat Reader. It's now called Adobe Reader, I think. Anyway, I'm going to print that out 100% scale on a Canon inkjet onto thin card. So whilst that's happening, just mention the rest of the setup. I've obviously done the Veroboard layout. I've done that as well on Serif Draw Plus, and again printed that out as a reference. The Veroboard itself is very small. It's only 13 by 19 holes matrix, but of course with these PIC processors you need very, very few external components, and they're mainly just resistors to limit current into LEDs and to the output of the device. In fact, it also uses the comparator that's provided within the chip as the detector, as the trigger detector, which is quite sensitive, about 200 millivolts sensitivity. So that's about right for feeding it from a line output of an audio mixer or whatnot. So I've decided not to build any additional microphone preamplifiers or anything into this box. The box, when we get out to seeing it, is a small ABS box bought from Maplin's. The programming all done in Great Cow Basic, which compiles down. Come across a useful IDE for that, which can be downloaded for free as well. So all pretty good, and that IDE recognises PicKit 2 programmer. So here's the printed out sheets. I'm showing upside down for some reason there. Anyway, now we'll prep the case and cut out the sheets from the thin card, which is quite an exciting thing for you to look at. Going to be spending some time doing this. I've decided that I'm going to use acrylic sheet to cover this panel plate, because otherwise it'll get very grubby with those rotary pots or rotary switches. And so there we are. The thing's sized for 175 by 81 millimeters, which is the flat front panel area of this box. I've not shown anything of the circuit board itself in this section, but as I say, it's just got the one PIC processor, about half a dozen resistors on it, and a capacitor, which PIC appears to require across its power. Right, here we go. Here's the things cut out, and the lower one is the drilling template. So I'm going to take that drilling template and going to apply to that double-sided sticky tape, which is shown applied here. It's only fairly narrow stuff, so I'm going to put several strips, but I am going to make sure that the whole thing is all tacked down, because if I just tack it in the corners, it's bound to ruckle up when I come to drill through it, which is what I'm going to have to do. So there we are. That's all the tape in place. Really good trim off there, and when I've done that, should be able to get it onto the acrylic sheet. There's a local supplier of that, can buy it as offcuts, but I've got a couple of 1 foot square sheets to work from, and fortunately it's been cut nice and square, or relatively square, by the supplier. However, the chances of me actually applying this sticky item accurately is probably pretty small, so let's see how we get on. Plonk the thing down there. Well, it's nearly square on anyway. I'm going to make sure that's well stuck down to the protective layer, which itself is stuck onto the acrylic sheet. It's got protective layer both sides, which is essential, otherwise we get badly scratched. Now I'm going to mark some lines for me to saw the thing down to, just to give me a little bit of space there for getting it absolutely square using a belt sander, a bench mounted belt sander. It's done a pretty good job, so let's see what the results are. Now the holes there have been made by drill and by one of the stepped hole cutting drills, which is far less likely to crack the acrylic, which is pretty brittle if you catch the corner of a drill flute on it. So that's sticking the thing on top of the box. I could have used 2 of those drilling guides and just glued one onto the box, but I've decided here to use the acrylic sheet as a template, just in case there's any errors in my drilling the holes. So kind of invent some center points there to drill to, and all seems to go quite well, really, surprisingly so. Got a scratch on the acrylic sheet from attempting to use a knife to deburr the holes, which was crazy. I should have used a handheld countersink drill. And there we are, that's the sandwich of the 3 items. So I'm going to jump forward a bit now to a completely constructed box with its front panel controls, and the other side there is the trigger in, the immediate out, the trigger out to the flash and a power supply input. There's a rear of the unit, see things stuck down with hot melt glue. That's the board itself, very small, and the resistor ladder chains that you see on each of the 3 12-way switches, but limited to 10 positions. And there's the output panel there from the rear. Next thing, we'll perform a very basic functional test, and here you can see you can switch the thing on, the power light comes on, it goes to locked, you press the arm button, the armed light goes on, do a manual trigger and it goes to locked, and the cycle repeats. Now we're going to do a set of actual delay checks using a counter timer and a scope so we can see the output pulses, and I'm still using the manual trigger here, not using the external trigger input, and it's showing that the shortest delay I can do is about 1.6 microseconds. 11.3 is what you get when you dial in 10. 20, that's looking pretty good. 29.7 for 30. 39.3 for 40. 49 for 50. Notice there it's not taking it up there. 58.7 for 60, so it's beginning to deviate slightly. 68.4 for 70. 78.1 for 80. Just checking that again. Now it's 87.7 for 90 microseconds. Now try the times 100 microseconds. 97.3 for 100. 194.1 for 200. 290.8 for 300. 387.6 for 400. 484.3 for 500. 581.1 for 600. 677.7 for 700. 774.6 for 800. 871.2 for 900. It's drifting off quite a bit there. Here's 967.9, just under 1 milliseconds for a millisecond. 1.94 instead of 2. 2.90 instead of 3. 3.87 instead of 4. 4.83 instead of 5. Messing about there. 5.8 when set to 6. 6.76 when set to 7. 7.73 set to 8. 8.69, nearly 8.7 when set to 9, and dialing in full house there, 9.65 milliseconds. Remaining tasks then, to add the thyristor, add a battery box, and of course take some pictures.